In this video, we will discuss series and convergence, and we're given a lot of basic stuff here, right? First thing, and first part, an infinite series is defined to be the summation of a sequence with an infinite number of terms. And notice that with our sequence, we're going to have that notation there. And so with a series, the big difference is here with the series, notice how we're listing out each individual term. We are adding each one up. And now we're going to talk about partial sums. And with partial sums, you see that here you're just taking part of the sum. That's why you have your partial sum. And we will find that a sequence of partial sums converges, then the series will also converge. And so we will talk about geometric series and telescoping series, and then we'll get to P series and harmonic series. So we do have a couple of different ways to look at these. Now, also looking at the difference with a series, notice that we have each term listed out in addition form here. So we have a half plus a fourth plus an eighth and so on. However, the sequence, that's really going to be of partial sums. So of course our first term will be the same from here to here. But for our next term, that 3/4 in our sequence, that's going to be the sum of a half and a fourth. So that sequence is sequence of partial sums here. And so that's a good way to look at the relationship between these two, because you have your series and then you have a sequence of partial sums. And so here, again, to get to 7/8, well, that's going to be a half, a fourth, and an eighth added together to get that third. So this is going to be S sub 3, which is going to be A sub 1 plus A sub 2 plus A sub 3. So that's going to be the idea of the sequence. And then this last part, the value of a series is the limit of the sequence. So this is a pretty important idea here. So again, the value of the series is the limit of the sequence. So our summation here, where we're going through and adding each term, our series, notice that that's going to be the limit of the sequence, and right there is our sequence. So we have a lot of major concepts here for us to practice. Alright, so for our next example here, we are asked to write the indicated partial sums, so S of n, for this series. So with our partial sums, notice for the first one, S sub 1, they just want us to list out that very first term pretty much in that sequence, and for the series, we're going to have the same. So that's going to be 1 over 2 to the 1 minus 1. And so that first term there is going to be 1. So for the next partial sum, we're going to have S sub 2. And so for S sub 2, we're going to have our previous 1 over 2 to the 1 minus 1 plus 1 over 2 to the 2 minus 1. And so we're going to have 1 over 2 to the 0 plus 1 over 2 to the second. Our third partial sum here of the series is going to give us 1 over 2 to the 0 plus 1 over 2 to the first plus 1 over 2 to the second. And so here notice that for our nth partial sum, that's going to give us 1 over 2 to the n minus 1. So we're going to generalize there for that nth partial sum. Okay, so here the idea of a convergent and divergent series. For an infinite series, the nth partial sum is given by, and notice here, it's just part of the sum of that infinite series. So if the sequence of partial sums converges to S, then the series converges to S. And again, right here, another major part, the limit S is called the sum of the series. Is if S of n diverges, then the series diverges. Very important concept there. Alright, so our first major series that we'll talk about is a geometric series, and in particular, this is going to be an infinite geometric series. This is huge for us to know. So there we have an infinite geometric series, and as long as our ratio, the absolute value of my ratio, or what I'm multiplying by each time, is that absolute value is between 0 and 1, then we can say that this series converges to a sum, and that sum can be found by a over 1 minus r. A is going to be the first term, and then r is going to be my ratio. And again, this is only going to work when that ratio, the absolute value, is between 0 and 1. Now we can do a partial sum of a geometric series, and that's going to be given to us by this formula here. Okay, so for these next couple of problems, we're going to look at an infinite geometric series and answer the following questions. So for the very first one, we need to find a sum 1, which is the first term of our series, so we see that's going to be 8. What is r? That's going to be your ratio, or what you're multiplying by each time. And so for this case, it looks like my ratio is 1/5. And so for our next problem, they want us to write our explicit rule for a sub n. So we need to try to figure out what is going on with this. And so our explicit rule, we're going to have our sum from n equals 1 to infinity. That's usually where we start with that. Nothing says you have to start at 1. It just depends on how you define the rest of it. And so for this one, we're going to say that's really 8 times 1/5 raised to the, we can't really say n because that first term doesn't have that 1/5 in it. So we're going to say n minus 1. Or we could start this series n equals 0 to infinity, and then we could have had 8 times 1/5 to the n. So it really just, whatever is going to generate those terms, you just have to be careful with. Now my fourth partial sum, so S sub 4, that fourth partial sum, is really going to be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. That's what that one's going to be. So a couple of ways to do that. One way, you could list out all of those terms. So you would have 8 plus 8/5 plus 8/25 plus 8 over 125. So that is one way you could do that, and that's going to give you 1248 over 125. Okay, for the next problem, we're going to find our infinite sum, and again, that infinite sum, that formula is going to be a over 1 minus r, and so we have enough information here to find that. So a is our first term over 1 minus our ratio. And so that's going to give us 8 over, that's going to be 4/5. And so we're going to cancel that. And so this is going to give us 10 for our sum. Okay, now the next part, they want us to find the limit as n approaches 0 of our S sub n. So here, that's going to be talking about our general term. So we have the limit as n approaches infinity of, and this is going to be 8 times 1/5 to the n minus 1. And so that's really talking about here 8 over, we can rewrite that limit if we need to, n approaches infinity of 8 over 5 to the n minus 1. And so notice that this is growing, the denominator is growing without bound. So this is tending to 0. For our next two problems, we are told to find each of the following if it is possible. So we need to find these sums. And so again, this is all going to hinge on our formula, that infinite sum formula of a over 1 minus r. And so for this part here, this first one, just like anything else here, to find our first term, that we're going to plug in that 0. So a is going to be 2 over 1, which is going to give a times 1 over 3 to the 0. So that looks like that's going to be 2. And so our ratio is really right here. We can rewrite that really for that ratio to be 1/3 all raised to the n. And we see that that ratio is bound. The absolute value of our ratio is bound between 0 and 1. So now we're ready to find that sum. And so for this first part, we're going to have 2 over 1 minus 1/3. So that's going to be 2 over 2/3. And so that's going to end up giving us 1/3 there. So here, that first part is 1/3. Now let's go find the other sum. And so for this one, we can do some rewriting to help us see what's going on with it. So I would rewrite this to infinity. And that is really the same thing as 2 to the n times 2 to the negative 1 over 5 to the n. And then that's going to be rewritten to be 2/5 raised to the n times 1/2. So that's going to help us here in our writing. So we can pick out our first term. Looks like it's going to be 1/5. So I have 1/5 over 1 minus our ratio. And we can see from here our ratio is going to be 2/5. So that's going to give us, so we're going to have 1/5 over 3/5. And so let's see what that's going to give us. So those 5s will cancel, and so we have 1/3. And so back over here, that's not going to be 1/3, that's going to be 3. And now we're going to add those. So 3 plus 1/3, that's going to give us 10/3. All right, moving on to part B. Again, the same idea. And here we can separate this out. We're going to have n equals 0 to infinity. And we're going to separate this or decompose that fraction to 4 to the n over 5 to the n minus, and here n equals 0 to infinity of 7 to the nth over 5 to the nth. And this term right here looks awful suspicious because of that 7 over 5. And if we look at this a little bit closer, notice that that ratio 7/5 all to the n, that's going to be greater than 1 for a ratio. So there's no way for us to find the sum here. So really this is going to diverge. It is not approaching a value. Okay, some different facts about series. Given two convergent series where A and B and C are real numbers, and notice what else it tells us. If the sum of this series is A and the sum of this series is B, then the series converge to the given sums. And notice all of the different manipulations we can do with those. Alright, so for our next problem, we're going to look at telescoping series. And so with that, we end up seeing different things that are going to happen with these series. So for the first, we will go through and look at our individual terms. And so really what's going to happen here, and this always is true with telescoping series, is that if we look at each individual term, we can break this apart. So for this one here, that's really going to be the same thing as 1 minus a half. That's going to be that first term. Plus, and then our next is going to be a half minus a third. And that's going to generate this term here. Plus, and then the next one is going to be, here keep in mind that's going to be 1 over 3 times 4. So that's going to be a third minus a fourth. And so if we continue this pattern out, I'm going to see that we end up with 1 over n minus 1 over n plus 1. That's the pattern that we have for this series. And so when we go through, notice that these values are canceling. And so we can extend that all the way out here. And so with this, then notice that we end up with 1 minus 1 over n plus 1. So now we can go ahead and find what our limit is going to be. So we're going to find the limit as n approaches infinity of a sub n. So for that, it's going to be 1 minus 1 over n plus 1. So notice that this is going to shoot off to 0. So we're going to end up with 1. All right. So now let's look at the next part. And again, before we go there, do keep in mind what we just found. We found the limit value of, and I'm going to write this out. This is the limit of the series, because this is going to be important for us to remember. All right, so for our next, they're asking us to explain the difference in the sequence and the series. So we've got a sequence and then we have a series. Now what we need to remember for our sequence here is how we get from one term to the next. And that's one of the very first things we talked about. So for this, when we're doing our sequence, if we plug in 1, notice that's going to give us 1 over 2 plus, or comma, sorry. And then if we get to 3, that's going to be our next term. So that's going to give us 1 over 2 times 3, or 6. And then our next term is going to be 1 over 12. And so on. So this looks like here, this is going to converge to 0. In other words, you're asking yourself, with this part here, what value is this heading to? Okay, so that's why we're saying, okay, this looks like it's going to try to converge to 0. And so now let's go look at this other side. Let's look at our series. And so if we have our series, and again, we're going to have n equals 1 to infinity. Notice with the series of a sub n, that's going to be 1/2 plus 1/6 plus 1/12, and so on. But notice what we're saying this is. If we look at that, then we see that our sum of all of these, if we go through our sum, we said that sum is going to be, and we can go through and find that, but I think we did. We said that sum is 1. And notice, that's going to connect what we said earlier back in the very first, that the limit S is the sum of the series. So notice we are showing that to be true here. So again, that limit of the series is actually the sum of that series there. So do keep in mind that as you're going through, we can see that's fact, that to be a fact for these. All right, for our next problem, we are asked to rewrite this as the ratio of two numbers. So let's write out what we see about 0.05 repeating. If we were to extend that, that would be, let's see, 0.050505, and so on. So we can look at this in each digit. This is your tenths, hundredths, thousandths. So we're going to have really 0 over 10 plus 5 over 10 squared plus 0 over 10 cubed plus 5 over 10 to the fourth. And I think we see now what's going on with this. So really, this series can be just written as 5 over 10 squared plus 5 over 10 to the fourth, and so on. So what we can do with this now is, if we could find the sum, then that would probably give us our ratio of our two integers. So to find our ratio, because we have our first term, we know this is going to be our first term. So the ratio here, what are we multiplying by each time? And it looks like we're probably multiplying by 1 over 10 squared each time. And that's certainly bounded between 0 and 1. So let's see if we can fill in our sum formula, that infinite sum formula. We have our first term, which is going to be 5 over 10 squared, over 1 minus our ratio, 1 over 10 squared. And so it looks like that's going to give us 5 over 10 squared over 99 over 10 squared. And so those 10s will cancel. So that ratio is going to be 5 over 99. For our next series test, we have what's called the Nth Term Test for Divergence. And this is really just talking about whether or not a series diverges. So notice that it tells us that here, if a series converges, the limit of its nth term must be 0. So if I have a convergent series, I know that limit is heading towards 0. Well, okay, but the contrapositive gives us a useful test for divergence, and this is so important. It's telling us that if the limit does not converge to 0, then the series must diverge. That is so important for us to remember. So before we study or go through and try to talk about whether or not a series converges or diverges, we have to realize that that nth term, that limit of the nth term, if it does not equal 0, then we're told that that series will diverge. All right, so for these first few problems here, we're asked just to determine whether or not this would converge or diverge. So here, the first thing we are going to do, even though we've given all of this, we're going to do our nth term test. And that's going to say that the limit as n approaches infinity of n squared over 5n squared plus 4. We're looking to see what that's equal to, and notice here your exponents are balanced. So this is going to be equal to 1/5, and 1/5 is not 0, so we know that this series here will diverge. That's really it. It's going to shoot off, and we don't know where it's heading to. It's not heading to 0, so we can say this will diverge. All right, so let's go to part B. Now for part B, we're going to do the same thing. We're going to look at an nth term test. And so with that nth term test, we're going to say the limit as n approaches infinity of n over n cubed plus 1. So looking at that, again, notice this time that denominator is growing a lot faster than the numerator. So here, this one equals 0, but we can't say, aha, this converges. We can say this may converge. We don't know if it does or not for sure. We're just saying that may converge. Okay, so now let's look at C. And again, the same nth term test. So we're going to say the limit as n approaches infinity of 1 over n. And again, I know that limit is going to be 0, but this one may converge. Now, the problem is here, even though those limits are heading to 0, let's look at some terms of this series. So in other words, let's look at what this is going to generate. Well, if we plug in 1, that's going to give us a half. Plus, if I plug in 2, that's going to give me 2/9. If I plug in 3, that's going to give me 3 over 27. And just for grins, let's plug in 4, so that's 4 over 65. So notice this is very quickly, we can say this is quickly approaching 0. If we graph this, we're going to see this graph doing all kinds of stuff, but as it gets bigger and bigger x values, it's going to get really close to that x-axis. So this one will converge. This series here does indeed converge. But let's look at the terms of this one. So that's going to be 1 plus a half plus 1/3 plus 1/4 and so on. So notice this one may be approaching 0, but it's not approaching it very quickly. And so for this one, this is actually going to be divergent. This is going to diverge. If we looked at the graph, this will eventually run parallel, but it's not going to be heading towards 0 as fast as B is. So we're going to say B does converge. It's heading towards 0. But this one, this is not going to converge. This is a divergent series, and it's an important one for us to remember. For our next problem, we're going to be asked to find a rule for a sub n. Now we're given that the nth partial sum of this series is given by this part here. So let's get an idea of what this is talking about. So if we talk about the nth partial sum, so let's say n is 1 to infinity of a sub n. So this is talking about a sub 1 plus a sub 2 plus a sub 3, a sub 4, and so on out to a sub n. So if we're talking about our partial sums, though, keep in mind that all of this part from here all the way out to here, that is S sub n. And let's say we take a small portion of this, that's going to be S sub n minus 1. Let's say we want all of its S sub n, and then everything up until really close to the last part is S sub n minus 1. So it's fair to say that we can rewrite our A sub n is really going to be S sub n, all of it, minus everything up until that last term. So how is that going to work? How's that going to help us? Well, we know what S sub n looks like. So really, our A sub n can be S sub n, which is n plus 2 over n plus 5. minus s sub n minus 1. So in place of these n's, I'm going to put n minus 1. And then, of course, plus 2 over n minus 1 plus 5. And so this is going to be the very last term. This is everything up to that last term. So we're going to do some algebra here. It's been a little while since we've had to do that. So we're going to have n plus 2 over n plus 5 minus, and that this top is going to simplify to n plus 1 over n plus 4. And we can do our cross multiplying here and multiply across the bottom. So we're going to have n plus 2 times n plus 4 minus n plus 1 times n plus 5. And that's all over n plus 5 times n plus 4. All right, so we do need to FOIL out the top. So we're going to have n squared plus 6n plus 8 minus n squared plus 6n plus 5. And again, all of that's over n plus 5 times n plus 4. And so collecting our like terms here, notice those n squareds are going to cancel. 6n minus 6n. So we're left with 8 minus 5. So we have 3 over n plus 5 times n plus 4. And that's going to be finding here, again, that rule for a sub n. That's going to be our rule for this. So do keep that in mind. And again, this is all working with your partial sums. Okay, so for our next problem, here we've got the nth partial sum of a series here. And we're given s sub n is this. And so we need to find a sub 6. So here, using the same idea as previous, let's list out what that might imply. So we have, let's say for a sub 6, we know this sum from n equals 1 to infinity of a sub n is going to be a sub 1 plus a sub 2, a sub 3, 4, 5, and 6. And so if I want to focus on just a sub 6, then I'm going to look at our partial sums here. Every bit of that is s sub 6, and then up into this part right here is s sub 5. So it's safe to say that a sub 6 is going to be s sub 6 minus s sub 5. So if I take all of those and subtract out the first 5 there, essentially, so that's going to leave me with just that one term. And so here again, going through and finding that, then I know that s sub 6 here is going to be using this rule here, and that's why we're having to go this way. All we have is that s of n formula. So if I plug in 6 there, that's going to give me 6 squared plus 2 over 6 plus 1. And then that's going to be minus our 5, so 5 squared plus 2 over 6, or we're going to say 5 plus 1. And so we're going to have 38 over 7 minus 27 over 6. And so here when we put that together, we're going to have some ugly number, and I don't have a calculator in front of me. So you all can calculate that if you want to know that final answer.